My name is Doug Wright, and I've been an engineer at StoneAge for the last 20 years, and I've put together this presentation to help explain pressure loss and jet impact. So why does it matter? Well, it does matter because you need the proper pressure and flow to get the job done, and it can make the difference between working and not. I've been places where they've said, oh, we've tried water before and water just doesn't work. Well, you don't know what the person before was in there trying, so it can make all the difference. And at the same time, the correct selection of tooling can make the difference between success and failure, as we'll cover in this presentation too. So why pressure matters? Well, every material has a certain pressure below which water won't have an impact. Like I can take a fire hose out to the concrete pad out there and spray on it all day long or all week long and probably all month long and not do any damage to it. So I need to get my pressure up to a certain point where I start to affect that material. And this curve is an example for concrete where, like, at 5,000 psi, and this is efficiency on this side. So more efficient is less energy, of course. So at 5,000 psi, it takes a whole lot of energy to just get into that concrete. Whereas at 10,000 to 15,000 psi in this particular concrete, that takes the least amount of energy. Typically, the optimum pressure for any given material is in the range of 3 to 5 times the threshold pressure. And then why does flow rate matter? Well, if you want to go faster, okay, I've reached my optimum pressure, but I want to get the job done twice as fast. How can I do that? You could do it by increasing pressure, increasing power through increasing pressure, but the ideal is to increase power through increasing flow rate. So this takes an efficiency curve for a material by pressure. Again, increasing pressure here, going along the curve improves my energy usage. You know, I'm more efficient. Well, then these red lines represent what happens at any one of those given pressures as I start to increase my flow rate. So this is like a line of pressure, and then this is a line of flow, increasing flow at that given pressure. So you can see it's not exactly linear or straight across, but it does effectively improve your removal rate to get the job done with the increased power applied. So you can, again, increase power through both increasing the flow rate or increasing the pressure, or both. Oftentimes it's dependent on what pumps you have. If I've got a whole yard of 20,000 psi pumps out there, it's likely I'm going to operate at 20,000 psi and just increase my power applied by adding more pumps. Pumps can be operated together. You can manifold them together. This is 4 or 5 pumps tied together per system, and then that allows you to achieve a higher flow rate at a pump pressure. There are sometimes can be restrictions on increasing flow rate, so water availability or means of dealing with that water. If they say, well, we don't want more than 20 gallons a minute going into this vessel at any given time, so you might be stuck with increasing your power through increasing pressure. Higher pressure does bring higher operating costs and greater risk of damage to what's underneath what you're trying to remove, whether it's refractory or steel even. And for that reason, the maximum operating pressure may be specified by the job to reduce this damage. Like, so if you're cleaning, copper tubes, well, you're going to limit your maximum operating pressure because you can cut into copper tubing pretty easily with too high a pressure. The other part of going to higher pressure, for the same power, your orifice sizes get smaller. And since the deterioration of a jet through air through standoff distance is proportional to the orifice size, that means if you're going to operate at a higher pressure for the same power, you may have to get much closer to the material to be removed, which in some cases can lead to more complicated and often really specific tooling, so you can get the jets close enough to be in effective range. This is an example photograph from testing we did, and you can find the paper on this on our website for StoneAge. It illustrates what a high pressure water jet can do, particularly if left stationary on steel. This was the inside of a steel tube, and it takes less than 10 seconds to do this amount of damage if you're operating at 40,000 psi in a steel tube, if you sit on it for less than 10 seconds basically, or more than 10 seconds. At 20,000 psi you'd have to sit there for about a minute, but still, if you're not paying attention and the tool's stuck and you know, wondering what to do next, and you leave it at pressure, you can damage that steel tube. And when you're at pressures below 10,000, you're typically pretty safe. I mean, you can eventually erode steel materials, but it would be like 10 minutes or more. You'd have to leave it in one place. This is an example of avoiding refractory damage, or not. On the right is intact refractory, and on left was refractory where it was actually really poor condition refractory. We were operating at a pressure trying to minimize removing refractory, but because it was so badly damaged, we couldn't help it. The hard part was when they came back and said, well, we want you to take out all that refractory. It's like, well, we're set up to operate at a pressure that hopefully does not damage the refractory, so that made it really difficult to actually try and remove it. This is an example of that specialized tooling. This was in refractory removal, where we needed, for this type of hex mesh refractory, you need to be typically within a foot of standoff distance. Up to 2 feet can be effective, but it takes like 4 times as long. So to be within a foot of it and to maintain the impact required to remove it, it can require some special tooling to hold the jets within that foot or less standoff distance. Ideally, we know, like if somebody calls and says, I want to clean this tank, well, the first thing you ask, do you have any idea what it takes to remove that material? And so ideally you get the chance to test on a sample or have past experience that tells you, okay, well, last time we did this job at 8,000 psi and so many gallons a minute. Well, okay, I can work from that, and you know, the next question is, well, can I do that same thing from 10 feet away or not? So first of all, we have to kind of go through the whole pressure loss thing. And this is one of my illustrations for I'd like to show it, just showing like what we're doing with a water jet. It isn't just magic. It's like, no, we're putting this much power continuously flowing out of a nozzle. But getting that power, getting that water to the nozzle, and still not losing all the power due to friction loss is important. So as an example of why it matters, if say you have a 2-lane highway and it's filled with cars going 40 miles an hour, you can get 704 cars per minute out of town. To get the same number of cars in the same amount of time on a 1-lane road means those cars have to be going 80 miles an hour. And as we all know, it takes more fuel to drive down the road at 80 miles an hour than it does at 40 miles an hour. And that's due to the resistance of the wind and the tires on the ground and such. Well, the same thing applies to water trying to flow through a hose. The higher the velocity of the water, the greater the friction and the turbulence, whether you are driving your car down the road or the water is flowing inside of a hose. So what do we do about managing this? The effect of the inside diameter of the hose, it has the greatest effect. It's almost to the 5th power. And this is the equation for pressure loss. You've got length, which is just directly proportional to the length because there's no power there. The effect of the flow is almost squared. It's to the 1.85 power. But as you see, to the diameter is almost to the 5th power. So that is the strongest. So based on that, you should ideally use a bigger, larger inside diameter hose where possible. Particularly as a supply line, you may be limited by, you know, you're cleaning this small tube, so you can't stick a 1-inch hose inside a 1/2-inch tube. But getting from the pumps up to where you're cleaning the tubes at, that's the place to use a larger supply line. You can also use 2 or more hoses in parallel where possible. Or again, back to the tube thing, you have to reduce the flow rate maybe because you're limited to a 4mm hose. Well, you're not going to put 50 gallons a minute through a 4mm hose. And of course, you like to have the pumps as close as possible to the job where you're doing the work, which is managing the length of the hose. This is an example of where using those big pumps tied together. We have 3 pumps coming in. This is 3 1-inch hoses. Just the pumps are down on the ground at grade. This is up on the second deck. So we've got a 100-foot run of 1-inch hose per pump, and each pump's putting out about 70 gallons a minute. And then coming out we have 4 hoses, and then these are going to go all the way up to the top of the structure. So if you then so here's your 4 1-inch hoses running up the structure to the top deck, to minimize that pressure loss getting up to where the tooling is going into the vessel. Currently we're using 4 pumps tied together and 6 hoses up the structure on this particular job, and that's then supplied through an 1.5-inch hose to the tool on the end, doing 300 gallons a minute. And while we're operating 10,000 psi on the ground, through 400 feet of hoses, we're still maintaining 9,200 psi at the tool. This is an example of 2 1-inch hoses feeding a 3D tool for running about 200 gallons a minute. So each hose is getting about 100 gallons a minute through it. You do notice that if you're doing this with a 3D tool, a Y or a T manifold does not work, because your arms will come around and hit, or your jets will come around and hit your hoses. So they're a pain to put together because you have to stretch the hoses out, but it keeps them out of the line of fire of the jets when they're running parallel like this. This is the big 2D tool that takes the 300 gallons a minute through the 1.5-inch hose on the reel. So how do we calculate this pressure loss? Well, we've written several different calculators over the years, and we have a current very simple one I'll show you. You can look in the back of your hose catalog. It'll give you the pressure loss for a 50-foot length of hose at a given flow rate. Or you can always do a field measurement, where you run the pump at the RPM you'll be running at to produce the flow you'll be running at, with the hose, with your system intact but without a nozzle on the end. Of course, make sure you hang on to the end of the hose or tie it down really well. And then your pressure loss through that system is what the gauge at the pump reads. This is an example of the calculator. This shows you enter the inside diameter of the hose and the length and your flow rate, and that will tell you your pressure loss. Now, the reason I did it this way, see, it does not matter what pressure you are at. It only matters what your hose size and length and flow rate is. Now, what matters is, okay, if I'm at, my pressure loss is 2,000 psi, say, if I'm at 20,000 psi, that means I'm going to have 18,000 psi at the tool. Or if I'm at 10,000 psi, I'm going to be about 8,000 psi at the tool. That's where pressure comes into that, but for calculating pressure loss, it does not matter what pressure you're operating at. So the example of using 2 or more hoses in parallel. Again, the same case, a 1/2-inch ID hose, 200 feet long, and putting 30 gallons a minute through it, you're going to lose 2,050 psi through that 200 feet of 1/2-inch hose. But if I divide that flow, 15 gallons a minute, 30 divided by 2 hoses, so 15 gallons a minute through that same 1/2-inch hose, 200 feet long. I've got 2 of them in parallel now. My pressure loss is only 500 psi. So that's the effect of the pressure being squared on pressure loss. And it's not, you don't add the 513 plus 513 because you've got 2 hoses. No, it's like a parallel circuit. Your total pressure loss is still just 500 psi through those 2 hoses. This is an example of you're fixed by, again, your tube size that you're cleaning. Maybe you have to use 3/8 medium pressure tubing to fit inside these 1/2-inch tubes, in which that tubing has a ID of 0.2 inches, and you have a 20,000 psi 17 gallon a minute pump and 25-foot long lance. And based on your past cleaning experiences in this particular material, that it's really good to have at least 18,000 psi blasting this material to remove it effectively. So that means you need to limit your pressure loss to a maximum of 2,000 psi, since you've got a 20,000 psi pump and you need at least 18,000 at the tip. So if I try to take my 17 gallons a minute and put it through that lance, I'm going to have a pressure loss of 5,000 psi, which means I would only be at 15,000 psi, which isn't going to do the job. But if I reduce my flow rate to 10.5 gallons a minute, I select a tip that only flows 10.5 gallons a minute, I'm only going to lose 1900 psi. So I've maintained my 18,000 psi at the tip by reducing my flow rate from the 17 gallons a minute to the 10 gallons a minute. And do remember there are other pressure drops in the system that we're not necessarily accounting for, such as fittings and elbows and other things. Okay, I'm run through an example of using pressure loss calculation. So again, I'm going to take my, say, my 0.203 ID tubing, 203, and say I've got a 30-foot long lance. Enter my 30 feet long. Since it's tubing, there's not going to be any stretch. It's steel tubing. And just let's say I'm going to try and run 15 gallons a minute through that lance. I would be losing almost 7,000 psi through that lance. So I don't want to say, okay, well, if I have 10,000 psi at the pump, that leaves me with only 3,000 psi at the nozzles. Or if I had a 20,000 psi at the pump, that leaves me with 13,000 psi at the nozzles. Again, I want to get it down to where I'm about 18,000 psi at the nozzle, so I'm going to start reducing my flow until I get there. Let's try 12 gallons a minute. That reduced it to 4,500 psi loss, so I'm at about 15,000. But I still want more pressure at the nozzle, so I'm going to reduce that flow again. Let's try 10 gallons a minute. And I'm at 17,000 psi now because I have about 3,100 psi loss. So I got to go lower than that. Let's try 8 gallons a minute. 8 gallons a minute. Alright, now I've got 1,980 psi loss, which leaves me with just over 18,000 psi at the nozzles tips. Now if that lance had to have been 40 feet long, well, I'm back. I would have to reduce my flow even more to maintain my 18,000 psi. And there you see now I have 1,700 psi loss, so I'm 18,200 at the tip at a flow of 66.5 gallons a minute through that 40-foot long piece of 3/8 medium pressure tubing. Now for hose, particularly in longer lengths, let's say I'm going to run 13 millimeter hose. Oops, that'd be 1/2 inch. And I'm going to run 400 feet of 1/2 inch hose. I can say, okay, what's a reasonable flow that I can get through that? Let's say, alright, 10,000 psi at the pump. Let's see, what happens if I try to put 50 gallons a minute through that? Okay, I'm not going to make it because it would take 11,400 psi to get through that 400 feet of 1/2 inch hose with 50 gallons a minute. So obviously I don't want to be doing that. Well, what about the case where I'm going to run 2 hoses in parallel? Back up. So the hose stretch number in here is for tubing, steel tubing, obviously it's not going to stretch under pressure, but a high pressure hose does expand. The ID grows slightly. About 4% is what we found to be a good value to use. Of course it shrinks a little bit with that too, but the interesting thing is when we tested this, it actually, most of the hose stretch occurs in the first couple thousand psi, even for a 20,000 psi hose. So say at 4%, yeah, it's going to help me a little bit, but not much. I'm still barely getting anything left, 600 psi at the nozzles. So let's look at the case of 2 hoses in parallel to run at 400 feet, 1/2 inch hose, because I've got a whole bunch of 1/2 inch hose. So 2 in parallel, 25 gallons a minute each. That reduced my pressure loss to 2,300. Let's say I'm going to run 4 hoses in parallel. Well, that leaves me at 12.5 gallons a minute per hose. Now I've limited my pressure loss to 585 psi. So if I had 10,000 psi at the pump, I'd be left with 9,400 psi at the nozzles. Swivels and valves have a pressure loss associated with them as well. So for that, we measure, like go out and physically measure the pressure drop across a given swivel, and from that you can come up with a CV value for any given swivel. And if you look in our catalog, you will see that for a BJV swivel, it's got like a 4.6 CV. Well, this is how you use it. You take your flow rate divided by that 4.6 and square it, and that would be the pressure loss through that swivel. We'll go back to the Excel here real quick because it's on there too. So say I've got my BJV, I know it's got a 4.6 CV, and I'm going to try to run 100 gallons a minute, which is what we say a BJV can do, I believe. At 100 gallons a minute, that BJV swivel will lose 472 psi through it. Now, most of our flow ratings that we give for our tools are based on a reasonable pressure loss, typically around 500 psi. In some of the smaller seals, like in the Barracuda, that is actually a physical limitation. If you try to put more than 15 gallons a minute through a Barracuda, the water flowing through that seal is going to like grab it and suck it down and try to shove it through the nozzles. But for the most of the time with the bigger seals, it's just saying it's a reasonable pressure loss. So I know I can run 120 gallons a minute through a BJV, that same tool. I'm getting up there though. I'm getting up to like 700 psi loss. So that the 100 gallons a minute, 110 gallons a minute was chosen based on a reasonable pressure loss. So let's look at like a Barracuda, which has like a 0.43 CV, I believe. Obviously, I'm not going to get 120 gallons a minute through it. It'd take 78,000 psi to do that. But at our 12 gallons a minute, we're losing about 800 psi. That's typically the maximum flow that we say for a Barracuda, and oftentimes you're more around the 8 to 10 gallons a minute range. So 10 gallons a minute, you're losing 540 psi through that Barracuda. Okay, so then what other do we have to deal with to determine whether or not we can do this job? Now we know that a jet, as it travels through air, loses power, loses impact force. So what can we do about that? Can we calculate it? Yes, actually we can. So say I want to clean this tank with a 3D tool, and my standoff distance is going to be 5 feet or 60 inches away from the wall at the maximum. What can I calculate how hard I'm going to hit that wall? So we can calculate the relative impact of the jet on the wall. We need to choose an orifice size, in this case an 1/8 inch nozzle, which is at a standoff distance of 5 feet away, 60 inches. That distance in terms of that nozzle diameter is 480 times. So 480 times a 0.125 nozzle is 60 inches. So that is my standoff distance in terms of nozzle diameters. Now we can go out and measure the impact, relative impact of a nozzle with increasing standoff distance. This is an example of 2 different nozzle types and under 3 different conditions. So the best nozzle, we called 100%, and at a standoff distance of 500 diameters. Under that, with that nozzle at those upstream conditions, I'm going to still have about 60% of my impact left over at 500 diameters away. At 1,000 diameters away, I'm just under 40% impact. If I take that same nozzle, that's the difference in these 3 curves here. If I have poor upstream conditions with that same nozzle, well, even up close, I've already down to 50%. And at 500 diameters away, I'm down to less than 10%. So what we mean by that on those 3 curves is this taking the same nozzle through a nice long straight feeder pipe feeding the nozzle compared to going through a tool like say a pipe cleaning tool like a BJV and water having to turn 90 degrees and come out radially. That's pretty poor upstream. That water is, you know, having a hard time, and then it's got to turn 90 degrees and then come out into the jet versus, hey, it's not got a nice straight flow path to it. to straighten it out and reduce the turbulence and, you know, good upstream conditions versus poor upstream conditions. So here's the same nozzle again. Good upstream, nice conditions feeding the nozzle. That's our 100% performance. And with standoff distance at 500 diameters away, we're down to 60%. I take that same nozzle and put it in this poor upstream condition, and at 50 diameters away, it's already half the impact performance of that same nozzle with a good upstream. And again, at 500 diameters away, it's down to 10% impact relative to the best performing condition. Or comparing at 500 diameters away with good upstream, I'm at 60% impact, and with poor upstream, I'm at 10%. So that third curve in between those two, what's that from? Well, that is from putting this little flow straightener in the nozzle. That's not something to filter out dirt. It's actually this little vane thing in nozzles is a flow straightener. And that's what gives you this middle curve. You can take the poor upstream conditions, the same nozzle that, yeah, 50% of the best, and putting in that little flow straightener brings you back up to 80% of the performance up close, and at 500 diameters away it brings you back up to about 35% of the performance. One thing we do know is that putting a flow straightener in with good upstream conditions can actually inhibit the performance. So there are certainly ways of reducing the standoff distance, like using extension arms and a tool such as a pipe cleaning tool. But not only do those extension arms reduce the standoff distance, they also serve to improve the upstream conditions. So you can gain, you know, a multiplying effect really, because you're getting closer, but you are also improving the upstream conditions to improve the quality of that jet and thus its impact. This is the effect, even the shortest extension arms. This is with 3 different standoffs. This is up at 200 diameters away. This is at 500 diameters away and 1,000 diameters away. You can see even using a 2-inch long extension nipple will improve your performance at 200 diameters away from about 72% up to about 84%. And once you get up to about 10 inches long, well, I'm almost to 100% at that standoff up close. At my bigger standoff distance, 1,000 diameters away, well, I have to keep increasing that length, and I can still expect improved performance at the bigger standoff distance. So then, to use this as a calculator, we can write an equation based on these curves, and then we can just type it into the calculator and it'll tell us what our relative jet impact is. So back to our spreadsheet, this is an example from it. I can take an 057 nozzle at 12 inches away, and if I got 20,000 psi at the getting to the nozzle, my impact at the surface will be equivalent to 11,000 psi. I can compare that then to maybe an equivalent horsepower at a lower pressure, which would then be a larger nozzle. I got 10,000 psi through an 098 nozzle at 12 inches away. My relative impact at 12 inches away will be equivalent to 6,500 psi. So in this case, I would have more impact out of the 20,000 psi 057 nozzle than I would at 10,000 psi through an 098 nozzle for the same distance away, 12 inches. We'll go back to the calculator here. So I want to compare the same horsepower, of course. So I can come up here and say I've got 10,000 psi through an 098 nozzle, and since typically you're going to be running 2 jets on a tool, it's rare to run one if you're trying to clean something, a tank, like a 3D nozzle. So I got 2 nozzles, 098s, that's 300 horsepower. 20,000 psi through an 057 nozzle, 2 of those, that's actually a little less horsepower, so still about 300 horsepower through. So yes, we are directly comparing the same horsepower at 20,000 psi versus 10,000 psi. And so at 48 inches away, at 20,000 psi through an 057 nozzle, I've got an impact at the surface of 3,650 psi, and at 48 inches away with a 10,000 psi through an 098, we've got an impact at 3,400. Now, as I get further and further away, they actually come closer together, but as you get up closer, the 20,000 psi impact will increase dramatically relative to the 10,000, because I'm limited by a I've got 10,000 more psi at the nozzle. So 12 inches away, I've got 11,000 impact with 20,000 at the pump, and 12 inches away here, I've got 6,500 psi. And that's because it's a percentage of the pressure I have at the nozzle. So, if I'm 80% of 10,000 psi is 8,000 versus 80% of 20,000 psi is a bigger number. This calculator, the curve used for it was the poor upstream condition curve, which, is, remember, was the middle curve on the three curves. Other things we can calculate are how fast should the tool rotate, or what is our surface speed. If I put a tool turning 300 RPM into a pipe, how fast is that jet moving across the surface? Say I've got a BJV turning 200 RPM in an 8-inch pipe inside diameter. I'm going to have a surface speed. That jet's going to be moving across the inside wall of that pipe at 7 feet per second. If I take that same BJV with fast fluid turning 200 RPM and put it in a 30-inch pipe, it's going to be moving at 26 feet per second. It really becomes important if you're looking at, as you get into great big diameters such as tanks and vessels and stacks, where like 15-foot diameter in this case, to get, I know based on the material I'm trying to remove, I want to be moving at about 20 feet per second across that surface. I want that tool to only be turning 25 RPM. Again, we can go back to our calculator. Let's say for our 6-inch diameter or 8-inch diameter pipe, let's do, and say I got a 300 RPM BJV, I'm going to have 10 feet per second. If I put that same tool inside of a 4-foot diameter tank, we'll be moving 60 feet per second. So if you think about that relative to, like, if you had a shotgun and you're hand holding it, like how fast, 60 feet in a second, that's really getting with it. Now, we've also tested, and we know that a jet does deteriorate just as it deteriorates through distance with standoff. If you move that jet too fast through the air, it will also take away from the power of that jet. And typically we try to limit things to below 50 feet per second. That's where the curve kind of really went south on us for deterioration. But again, it can be based on the material. Like for coke removal, we know based on experience we want to be moving about 20 feet per second, because that's the dwell time we need to effectively impact that material to break it up. So in case of say a coker that's 20 feet in diameter, 240 inches, and to get my 20 feet per second, I don't want to be turning 300 RPM obviously. 30 RPM is about 30 feet per second. 20 RPM should give us about 20 feet per second. So I know cleaning this 20-foot diameter thing, if I know I want to be moving at 20 feet per second, I need to have a tool that I can have rotate at 20 RPM. The other thing we can calculate using this, say in tube cleaning, we can calculate the time it would take us to clean a tube, which we get asked. So say I know I've got say a Banshee, and it's got 18 orifices in it, a polisher head maybe, and say we put 4 jets in that hit tip, and jet spread is like, well, what's, once that jet exits the orifice, it spreads out. It's not 18 thousandths worth wide of impact. But obviously, the fuzz you see isn't effective either. But typically you can figure at least twice on your jet spread, 2 to 4 times. And then say for a Banshee turning 20,000 RPM, I can run through that tube at 240 feet per minute, which is pretty fast. Let's take a more reasonable example. Let's say I've got a lancing machine. I can calculate how long it will take, because the lancing machine turns about 500 RPM, and I've got 4 jets 018s. I can move about 6 feet per minute. So if I had 20-foot long tubes, it's going to take me about 3 minutes to clean those. If I had to hit every bit of those walls, at least with a jet spread of 2. Of course, if I double my RPM, I get to 12 feet per minute. Effectively, I just doubled how fast I can go. So a 20-foot long tube will take 2 minutes because I've doubled my rotation speed. Or if I say, well, my jet's actually effective 4 times its diameter, again, that's going to effectively double my feed rate. Or if I know I really want to hit everything really hard, like hit everything twice and make sure I'm getting it, I can put in a 0.5 for my jet spread, which is effectively hitting everything twice, and that means a feed rate of 3 feet per minute, so really slowing it down. Other things we can do, well, if we happen to have a material, we've got samples of a material, we can test on that and determine, you know, what is its material removal rate. So this is for like 4 different types of refractory, just running across them with a single jet, and you know, at a given speed and pressure and flow rate, you can calculate how much volume of material you removed in that single jet pass, and then you can come up with a value for that. We do this for concrete as well, and then you decide, okay, I'm going to run you know, 600 horsepower is what I'm going to use on this particular type of refractory. And if I know a given volume of material, then I can calculate the time based using this factor. It's like a constant. So my time that it's going to take in minutes is going to be my volume I got to remove, however many cubic inches I need to remove based on thickness and surface area, times this factor, divided by the power I'm going to use, which in this, you know, say 600 horsepower. That will actually tell you how long it will take to remove that material in actual running time, which can be as low as 10% of actual whole time you're there. Anyway, it's a useful number for estimating and planning. Okay, back to the original second slide there, where it said something about the selection of the proper tooling can also make a big difference. So when it comes to applying really high flow rates, we've had some experiences in this where we went 1 year and completely failed, and came back the next year with a different strategy, and we completed the job effectively. For that example, we were trying to run 3Ds the first time, which were limited to a maximum flow rate of about 200 gallons a minute with a loss of about 1100 psi. Well, we came back with a 2D that capable of running 300 gallons a minute with a loss of only 300 psi. So right there I'm applying a third more of the power with a third less of the pressure loss. The other difference between a 3D and a 2D, if I'm trying to run in this large tank and it's so big I can only run near one wall at a time to be effective range, well, 3D, because it sprays up and down and all around, it's only making contact between 20 and 40% of the time the jets are within the effective range of impact. Or a 2D in the same situation can make contact between 40 and even 100% of the time if you can put really long arms on it and put it down the center of the vessel. So all that adds up to at least 50% more time that you're in range, and at least 70% more power applied with a 2D versus 3D. And that was a perfect example of how going in with the proper tooling can make the difference between success and failure. Well, thank you for your time, and I hope you enjoyed this presentation, and I hope it was useful to you.